Good afternoon, this is Schweitzer. We're going to look at, in this video, a little more straight calculations, almost very few examples of the calculations. Just show you kind of how you go about doing them, and then we'll have another video after this, just walking through some examples. Our first thing we're looking at here is going to be just involving how we go about estimating entropy. Now, of course, entropy is, I think of it just kind of like a form of energy tied up in order. So entropy is basically movement. And when you have more movement, then you get more entropy. So if a reaction goes from a solid to a liquid, that's increased movement. That means positive. If it goes from a solid to a solid, okay, well, might be some change, but not going to be very much. You go a gas to a gas, but it goes from one gas to two gases. Well, that's also an increase in entropy. So one gas particle goes to two gas particles. So that's another way we kind of can estimate movement, just by the state that we're in. That's a lot of it. And you go on your entropy tables and the thermodynamic tables and look at how much actual movement there is for a solid. It's very little, very low entropy. Yet for gases, the number is relatively large. Okay. Few things we might want to point out to is, can you have a zero entropy? And the answer, entropy, and the answer is yes. All right, so that would be a perfect crystal at 0 Kelvin. So it's not a relative scale, and we can have zero entropy. Okay. So our change in entropy is actually based off 0. Different than delta H and delta G. Okay, so estimate. So let's try these out a little bit here. You should try them on your own. I'll do maybe one or whatever. You try them on your own as best you can. What's happening to the movement over the course of the reactions? 2 gases to 1 gas. That's a losing movement. Okay, if that makes sense, you try the rest of them on your own. I have 6 total gas particles here, and I have 7 over here, and therefore we are increasing movement. Solid to liquid, losing movement. Liquid to a gas, gaining movement. Aqueous, they're moving around a little bit in there. They're able to move to a solid, which would be losing movement. Solid and gas, or just solid, would be losing movement. And there you go. All right, so I can estimate the sign of S. Can I calculate it? There are a couple ways you can calculate this thing. One is just by the same formula that we used before. A couple of things about this is using your thermodynamic tables, and it's done the same way as the other ones. Notice there's no delta here because it's not based off a relative scale. Therefore, go ahead, grab your thermodynamic tables and try this one out. Remember, step 1, we get our data. Step 2, we multiply by the coefficients because it's on a per mole basis, and 3, we do the product minus the reactants. Go ahead, try it, and here's the answer. All right, get our datas here, and notice that solid's got a pretty low entropy. Not 0 though, because these are relative scales. This one is not. Gave your stuff. Everything is 1, so there's no multiplying needed by the coefficients. Sum up all your products, and then you do your products minus your reactants. And a positive 2.26, so a slight gain in entropy, but not too much. All right, how else can I calculate entropy? Well, in this case, with this formula, as long as you're given these guys, then you can solve for this one. Okay, that should be self-explanatory. A couple things I might mention to you as well, just to remind you, is that this guy is in kilojoules, this guy is in kilojoules, but this one right here, entropy, is in joules. So when I'm running off this equation, sometimes you might see me put divide by 1,000 on there. That's if you come from the tables, you need to flip that from joules per Kelvin into kilojoules per Kelvin. Okay, just heads up. All right, so again, this is a summary here. Things can you estimate? Can you calculate with the right tables? And can you just use the Gibbs free energy equation to solve out for that guy? Okay. All right, what about calculating delta G? All right. Well, first of all, keep in mind, what are our little prime symbols there mean? That means STP. In this area, STP is 25 degrees Celsius, which is 298 Kelvin. It also means 1 molar. It also means 1 atmosphere. So there's a couple different conditions that you'd go by, but it means STP. So the tables are all at STP. So both products and reactants are all 1 molar. Everything's equal. These would always have a little prime symbol by them. And you can only do STP off the tables. So how do I calculate ΔG at standard pressure? Well, I can use the tables. Or I can put in here 298, and so if I would need these guys then, okay, and I could solve for that guy at STP. How would I get ΔG at a non-standard temperature? Typically speaking, the way we would do that is we'd use this formula, and we put in a new temperature here. We don't always have information about delta S and delta H at non-standard temperatures, so we typically just use the standard version. This is not necessarily the best, but we go with it. But we should understand that if we use this at the entropy and the delta H at the standard temperature, then altering this temperature, that this is going to be somewhat flawed, and that should be aware that that is an issue. Okay. Other than that, that's basically an overview of the calculations you should expect to be seeing. Thank you.